Yeah, I think that we can start our seminar today. The time is unusual. It is a pleasure to greet here Andreas Reisneger, famous scientist who possibly doesn't need an introduction, but I will say a few words about him. He graduated from the University of Chile in Santiago in 1988 as a master in physics, and then he got a PhD student position in Caltech for 5 years. He defended successfully and got a position of postdoc in Princeton for 2 years and then returned to Chile. And in Chile, Andreas worked for many years, more than 20 years, at the Institute of Astrophysics of Catholic University in Santiago. And then now he is working at the Metropolitan University of Science and Education this year. So Andreas is a very famous scientist who is very broad, working in physics and astrophysics, cosmology, mostly theoretical, but likes to explain observational data. He has more than 100, exactly 123 publications with many prominent scientists. First of all, with Peter Goldreich, this, well, very famous theory of magnetic field decay in isolated neutron stars, published in 1992. For us, it is very good that Andreas is collaborating with a team of scientists from the Ioффе Institute. The team leader is Michael Gusakov, and we are very glad to see Andreas here with the talk. Today, the title of the talk is about here to fluid simulations of the magnetic field evolution in neutron star cores in the weak coupling regime. Please, Andreas.
Thank you very much, Professor Yakovlev. I'm very happy and very honored to have been invited to give this talk. For many years, I have known you and other members of the Ioффe Institute, which certainly is one of the main places in the world working on neutron star theory. And so I'm very glad to be collaborating with some of your institute members. I also have very nice memories of visiting your institute. So yeah, so it's great to be in contact with all of you and to be giving this talk. So the title of the paper that you asked me to discuss in this talk is rather complicated, and I will try to make all of it clear in this talk. You also told me that there is a wide range of expertise on the topic in the institute. I know some of you are, of course, world experts in the topic, and I don't know whether you will get too much out of the talk. Others are not, so I hope to make it understandable and useful for everyone. So this paper was written by a collaboration of 3 people, all of us at different institutions in Santiago de Chile. The first author is Francisco Castillo, who is a postdoc at Universidad Católica and who did all the simulations that are included in the paper. And also some of the slides that I will be using come from him. I would also like to point you to the acknowledgements of the paper, where the first person mentioned is Mikhail Gusakov, who certainly contributed in an interesting way to the discussion of these things. and we are collaborating more intensively since then. We met personally in January here in Santiago, and since then we have been discussing over video conference. And well, other people have contributed also with the discussions, and there are several Chilean funding agencies mentioned that supported some of this work, including Michael's visit to Santiago. The outline of the talk is, I will first give a fairly long introduction, briefly motivating the discussion of magnetic field decay in neutron stars, and then going into some detail into stable stratification, hydromagnetic equilibria, and stability of these equilibria in stars generally and neutron stars in particular. And only then I will go into this paper, particularly where we do fluid dynamics in neutron star cores, where I will talk about the role of neutrons and charged particles and the relative motion, which is called ambipolar diffusion, and the role played in our simulations by real and fictitious friction forces. I will certainly show some of our simulation results and talk about the work left to be done. So, as most of you probably know, the main way in which we get access to the magnetic field of neutron stars is through their spin down. Neutron stars are observed as rapidly pulsating objects, which in fact are not pulsating but rotating, and they so from the rotation we get we see pulses. And we can see that these pulses progressively become slower, the frequency becomes lower, and then from measuring precisely the frequency and its derivative, or the period and its derivative, which is of course equivalent, we can infer the magnetic field from a dipole spin-down model in which the magnetic field couples the neutron star to its surroundings and therefore makes it lose angular momentum and rotational energy. And we can associate it with this a characteristic time scale, which is basically the ratio of the period to its derivative, which is the time scale on which the neutron star is spinning down. That allows us to organize neutron stars on this classic period derivative diagram, in which the most strongly magnetic neutron stars are on the upper right. These lines correspond to constant magnetic field. Here we have 10 to the 14 Gauss, 10 to the 12 Gauss, 10 to the 10 Gauss, 10 to the 8 Gauss. And so on the most magnetic side, we have the so-called magnetars, which have the special property that their time averaged luminosity in the X-rays and gamma rays is substantially larger than the rotational energy they are losing. So they need an additional energy source, which is generally assumed to be the magnetic field. And on the opposite extreme, well, in the middle, we have the classical pulsars, some of them with supernova remnants, some for which the supernova remnants have already dissipated. And then we have this group down here, which are the millisecond pulsars, which are the fastest rotating, but also with weaker magnetic field and old ages. And here the big question is, why are the magnetic fields of these objects much weaker? And traditionally, this has been attributed to the accretion process, which is probably the cause of the fast rotation, in which the accretions where disk spins up the star. But it's not clear whether the magnetic field decay or apparent decay in these objects is associated with that or just with old age. So these are the two main motivations for studying how the magnetic field in neutron stars can evolve. There are others as well, but I would like to stick with these, which are the most important ones in my view. So for that, we need to have a model for the neutron star, and this classic model of the neutron star is what is shown here, in which we have a crust which has two different layers, but in all of them there are ions which are fixed in a lattice once the temperature becomes moderately low with after the very fast initial cooling. And there is a core, which is essentially a fluid, a liquid, which contains several mobile particle species. Likely, some of them are likely superfluids or superconductors. So there is a fairly complex dynamics here. In the crust, the only mobile charge carriers are the electrons, and that makes the equations for the evolution of the magnetic field relatively simple and at least well-defined, although non-linear, and therefore subject more to numerical than analytical studies. But that has been studied to quite some extent. Here I want to concentrate mainly on the core, which is where the two fluid dynamics that we are describing is going on. So one thing I wanted to point out is that, of course, in vacuum, and Earth is a vacuum for these purposes, neutrons decay spontaneously, and they are not long-lived. They decay in about 15 minutes. However, in degenerate matter, like in neutron stars, the low energy quantum states are all blocked, felt by the Pauli principle. And so there will be some neutrons present which cannot decay because the possible final states of protons and electrons are already occupied. And so eventually the neutron star matter will, these two reactions will occur, neutrons decaying into protons plus electrons plus antineutrinos, and protons plus electrons combining into neutrons and neutrinos. Neutrinos and antineutrinos escape from the neutron star. And so we will have an approximate chemical equilibrium in which the chemical potential of the neutrons is equal to the sum of the chemical potentials of protons and electrons. And at typical neutron star temperatures, these chemical potentials are essentially the Fermi energies. And so around nuclear densities, the neutrons will coexist with some amount of protons and electrons, typically a few %, but dependent on density. This fraction will depend on density. And of course, there can be more particles as well, as I will show next. And this is important because we have these particles, protons and electrons, which are charged and degenerate, which means that they can sustain electric currents which flow with very little resistance, and so the magnetic field will be frozen into these charged particles. It will be moving with the charged particles for a long time. The resistive dissipation time in the neutron star core is very long. So this is one possibility of how the core of a neutron star could look like. The horizontal axis is the baryon density increasing to the right, and we have some fraction of neutrons and increasing fractions of other particles as we go to higher densities, so that is deeper into the neutron star. So this has one important consequence, which is that the matter inside the neutron star is a non-barotropic fluid. What does this mean? It means that if we take some blob of matter and move it to a different position in the star, particularly to a different radius against gravity, for example, in this case, and we let it achieve mechanical equilibrium, pressure equilibrium with its surroundings, the composition of this blob will be different from that of the surroundings, because it will be remembering the composition it had at its initial position. And so with this new composition, the density will be different from the density outside, although the pressure is the same, or because the pressure is the same, but the composition is different. This means that there will be a buoyant force on this blob, which in principle could point up or down, and which will be characterized by this Brandt-Weisler frequency, where you have the gravity squared here and two derivatives of density with respect to pressure. One is the equilibrium derivative, which is what you get comparing the surroundings of this blob at the two different positions. And the other one is the adiabatic derivative, which is the derivative that you get as you move with the blob, which will, of course, be different from the analysis that I just showed. And so if this frequency squared is positive, we will get stable oscillations. This will be a stabilizing effect. The blob will tend to move back to its initial condition and oscillate around the initial position. If it's negative, it will be unstable. The blob will keep going and we will get convection. And if it is equal to 0, it will be neutrally stable. That is what we call barotropic. Or at least I will make this correspondence between barotropic and neutrally stable, which would mean that there is a unique relation between density and pressure, which applies both inside the blob and outside. In the neutron star, this will be a stabilizing effect. So matter will be stably stratified. It will be difficult to turn around different fluid elements. And the same is true in upper main sequence stars and in white dwarfs, where, however, the role that composition plays in neutron stars will be played by a specific entropy, which will have a gradient inside the star, but will be conserved as we move a blob to a different position. Okay, so this is something I want to stress, that inside neutron stars and also inside other stars, we will have this stabilizing effect of buoyancy forces. In the case of neutron stars, as I said, we will have stable stratification, and the Brandt-Weisler frequency can be estimated as being about 10 to the 3 seconds to the -1, which was first pointed out in a paper from my PhD thesis with Peter Goldreich, and simultaneously Dong Lai had been working on this. And this frequency is much larger than what I would call the Alfvén frequency, which is defined here, and which is the growth rate of magnetic instabilities, which even for 10 to the 15 Gauss magnetic fields, characteristic of magnetars, this will be only something like 10 per second, so it's much less than the buoyancy frequency. And this means that magnetic force generally can't overcome the buoyancy forces unless the magnetic field strength is 10 to the 17 Gauss or so, or higher. And this means that the buoyancy will help stabilizing magnetic equilibria. Okay, so this might play an important role in what the magnetic field in a star generally and in a neutron star in particular might look like. Now let's look at what a hydromagnetic equilibrium in a star could look like in general. We will have a force balance between the classic pressure gradient, gravity force. Psi is the gravitational potential, rho is the mass density, and the Lorentz force caused by the magnetic field. So we will have these three forces balancing. Generally, the Lorentz force is a small perturbation. This term is about 1 million times or more smaller than the other ones. It might be larger in the case of superconducting protons in a neutron star, but it will still be much smaller than these other forces. So in general, the Lorentz force is a very small perturbation. So we can decompose this equation into a background equation, which is the classic hydrostatic equilibrium without a magnetic field. And a perturbation, that is the Lorentz force, will cause a small pressure perturbation and a small density perturbation. In principle, also a gravitational potential perturbation, but we will ignore that here because it is probably not important. That is a classic Cowling approximation. Okay, so if we have a barotropic fluid, as mentioned before, we will have a one-to-one relation between pressure and density. And that means that the pressure perturbations at any given point will be proportional to the density perturbations. And this means that these two terms are not really independent of each other. There will be only one scalar function available for the fluid to balance the Lorentz force, and therefore we cannot choose an arbitrary magnetic field configuration and expect that to be in equilibrium with a fluid. There will be only very special configurations that are in equilibrium with the fluid. This will be somewhat different for a non-barotropic fluid, in which we have another variable like entropy or composition, which allows delta rho and delta p to be independent variables, because there is this other variable which can also vary and which relates the two. And so we will have two independent scalars in this case. Delta rho and delta p can be considered as independent variables, and so the equilibrium is much less constrained. It is still constrained because here on the left-hand side, we have a three-dimensional vector, a vector with three components. And here we have only two independent scalars to play with. So there will still be one scalar constraint on the magnetic field, but it is much less constrained than in the barotropic case, where these two are one-to-one related with each other. Okay, so in order to have a more definite model, we will think about axially symmetric equilibria. There are also other justifications for this, which I will mention a little bit later. So, in axially symmetric equilibria, you can imagine the magnetic field.
Sorry, can I ask a question?
Sure, of course.
In principle, in a slightly this deformed way, the pressure, this delta P, delta capital P, can be anisotropic, right? Why should it be scalar? So the in principle pressure is a tensor.
Well, in general, you could think of it as a tensor, but the non-diagonal components in this case are very small. Well, I have not thought much about this, but this is basically a fluid. It is very close to what relativists call a perfect fluid. So, for example, viscous forces are not important. So I don't think there will be any important non-diagonal components to the pressure.
Strictly speaking, pressure is scalar, as it's at least as it defined in Landau and Lifshitz, for example.
Thermodynamical pressure, yeah.
Yes, it's
Thermodynamic
there is stress tensor. It is another quantity.
Yes. Well,
but in force balance, you have the stress tensor, not pressure, right? Okay.
Oh, yeah.
Yeah, but I think that there is the question still has a point in the sense that I'm here assuming that the stress tensor is just a scalar pressure times the identity matrix.
Right. So my question was about this this constraint, which one scalar constraint. So
yeah,
there is some freedom in this stress tensor, which may somehow modify, but you say it's small. Okay.
Yeah.
Thank you.
Okay. So I will now concentrate, as I said, on axially symmetric equilibria. And then you can imagine, as in this picture here, where the central vertical line is the symmetry, the magnetic symmetry axis. And the lines generally, with the arrows, are the magnetic field lines or magnetic flux lines corresponding to what we call the poloidal or meridional component of the magnetic field. And we will have in the phi direction a toroidal component. So the magnetic field can generally be written in terms of two scalar functions, which are sometimes called the flux function and the current function. And there are different conventions for the letters used for this. I have traditionally used alpha and beta. And so it is useful to write the magnetic field in this way, where this is the gradient of the phi angle, of the azimuthal angle. So this is essentially a vector in the phi direction. And so alpha grad phi will be the phi component of the vector potential, and beta grad phi is the phi component of the magnetic field. And with both of them, we can construct the magnetic field in terms of a poloidal component and a toroidal component. And each of them, by construction, each of them independently satisfies that its divergence is equal to 0. Okay, now this equilibrium equation here, in axial symmetry, these two gradients on the right-hand side can only point in r theta plane. Both of them are poloidal, and they have no way of having a toroidal component. So the constraint that we still have in the barotropic case will be that the phi component, the toroidal component of the magnetic force, of the Lorentz force, has to be 0 in order to have an equilibrium, because that component cannot be balanced by the pressure gradient and gravity force. So if we impose that and replace this form of the magnetic field into this equation, we get the relation grad alpha cross grad beta equal to 0. So the gradient of alpha and the gradient of beta have to be parallel to each other, which we can write as beta being a function of alpha. It might not be a function in the strict mathematical sense, in the sense that it might have more than one branch, but locally beta will be a function of alpha, except perhaps at a few singular points. But this means then that, well, alpha is constant along poloidal field lines by definition. Well, from this way of writing the magnetic field. Each of the magnetic field lines has a constant value of alpha associated with it. And so from this relation, it also has to have a constant beta value associated with it. And so if the surroundings of the star are vacuum, there cannot be a toroidal field in this vacuum region outside. So beta must be 0 outside of the star. And since beta is constant along field lines, it has to be 0 along all open field lines. All the field lines that go outside of the star for part of their trajectory will have the property that beta is equal to 0. So everywhere that is white on this plot, beta has to be equal to 0. It can be non-zero only along the closed poloidal field lines, the field lines that close inside the star. On those, we can have a toroidal component of the magnetic field as well. Everywhere else, the toroidal component in equilibrium has to be 0. In principle, this is the only constraint that we have on an equilibrium magnetic field configuration in axial symmetry. There are no other constraints. Now, if the fluid is barotropic, that is, if the density is a unique function of pressure, which without any other variables intervening, in that case, we can define this enthalpy variable, which is an integral of dp over rho plus the gravitational potential. And in that case, the force equilibrium can be written in this way. Here we have the Lorentz force per unit mass. Note that we divide it by rho, which can be written as this combination, but this is just gradient of h. That means that in this case, the Lorentz force per unit mass has to be a gradient. Now, if we again have axial symmetry and we replace this in here, we can derive what is called the Grad-Shafranov equation, which is this equation given here. Well, first we get that that h has to be a function of alpha, just as beta was a function of alpha. And so these primes are derivatives with respect to alpha. And so we have this somewhat strange looking equation in which this operator is the so-called Grad-Shafranov operator, which is something like a Laplacian, but modified by the geometry here. And we have these terms in which we have these in principle arbitrary functions beta of alpha and h of alpha, whose derivatives appear in this equation. And so you have this rather complicated equation, which of course appeals to people with an interest in applied mathematics, and which I want to stress, however, that this characterizes only axially symmetric equilibria of magnetic fields in barotropic fluids. Okay, so that is what we can say in general about axially symmetric equilibria, both in the general non-barotropic case and in the barotropic case. Now, the question arises, of course, whether such equilibria are stable. Taylor showed a long time ago that a purely toroidal field is unstable. Basically, flux rings could slide with respect to each other, and so a purely toroidal magnetic field would not remain stable. And the same is true for a purely poloidal field. Again, you have flux rings which can slide with respect to each other, or you could do this Flowers-Ruderman construction in which you cut the magnetic field along the axis, and then you can turn one half with respect to the other. So both toroidal fields and poloidal fields are unstable, and this has been shown fairly rigorously since a long time ago. However, it was speculated for some time and then shown in simulations that you could have a stable equilibria in which you have both poloidal and toroidal fields, which is illustrated here or in these simulation results. These are results by Braithwaite and Sprout, and later work by Braithwaite by himself. And here, the poloidal and toroidal components of the magnetic field stabilize each other. You can think of the magnetic field lines like elastic strings, and here they are sort of tied together in a knot, which doesn't allow the magnetic field to really move much in any direction. So in this simulations, which were first reported by Braithwaite and Sprout in Nature in 2004, they simulated self-gravitating balls of conducting ideal gas, basically a star, or a model of a star, which were stably stratified by an entropy gradient. This has not been stressed very much, but I want to particularly stress it. These were stably stratified stars, and they started out with a disordered initial magnetic field, a very random magnetic field, and they found that generally these magnetic fields evolved into stable configurations, which in many cases looked like this. Later, Braithwaite found that if the initial magnetic field was closer to the surface of the star, he could also get more complicated equilibria. But in a fairly vast class of initial configurations, he had them evolve into these roughly axially symmetric configurations with both poloidal and toroidal magnetic fields.
Sorry, may I ask?
Sure.
There are only numerical simulations, yeah?
Yes.
Is it possible to describe this with some topological consideration or something like this, to formulate this like, well, elegant mathematical construction?
No, it has not yet been possible to do that. So far, these are only numerical simulations, first performed by Braithwaite. Now our postdoc Laura Becerra, who is also connected, I think, is repeating those simulations with a different code in order to check that we get the same result. But it has not been possible to prove, for example, through a variational principle, that these equilibria will be stable. And in fact, not all of these equilibria are stable. I will talk a little bit more about that. There are some conditions that the poloidal and toroidal components have to satisfy in order to be stable. In fact, I think that's the next slide.
Yeah, thank you.
You're welcome. So with our postdoc, Joe Mitchell, well, Mitchell basically assisted by Braithwaite and in lesser degree by some others of us, ran some simulation in which he compared what the magnetic field would do in stably stratified versus barotropic stars. So it was basically the same code that Braithwaite had used, but now he did some simulations in which there was an entropy gradient, so it was non-barotropic, it was stably stratified, but he also did some with a uniform entropy, and in order to see the difference. Here for reference, he shows what would happen if you had just diffusion. If you have no fluid motions that carry the magnetic field, you have just diffusive effects, which are also present in the other simulations. And then he ran several simulations with random initial fields, both in stably stratified stellar models and in barotropic models. And you see that for the stably stratified model that is shown here, the line, the evolution of the magnetic field is essentially parallel for the diffusion-only case, and it ends up in one of these toroidal poloidal equilibria. Whereas in the barotropic case, you see that after in a few Alfvén times, which you can see here on the horizontal axis, the magnetic energy decreases substantially, and you do not get one of these equilibria in the end. So in this case, that is with a random initial field. In the other case, we started with a twisted torus, this combination of poloidal and toroidal. And again, we get that in the barotropic case, these become unstable for many different parameter choices. Whereas for the stably stratified case, we have a much slower decay, which is consistent with diffusion only. So from these simulations, it seems to be that in barotropic stars, you don't have any stable magnetic equilibria. Whereas in stably stratified stars, you have some magnetic equilibria, but which, well, not all magnetic configurations are stable. And that is something both Braithwaite and Mitchell and others have explored, and Laura Becerra is exploring now. But so we have rough conditions for mutual stabilization of the poloidal and the toroidal component. For the poloidal component to be stable, the energy in the toroidal component must be larger than something like 1/4 of the energy in the poloidal component. Okay, that this inequality allows the toroidal component to stabilize the poloidal component. But then we need another inequality to stabilize the toroidal component. And the toroidal component is stabilized by a combination between the poloidal component and the buoyancy force. And the buoyancy force here is characterized by these two indices, capital gamma, which is the adiabatic derivative of log p with respect to log rho, and the lowercase gamma is the derivative between the background pressure and density.
May I ask?
Sure.
How these conditions have been obtained? From some analytical consideration or just, well, looking at many numerical simulations?
It was a combination. There are sort of hand-waving analytical arguments that you can give, and which are in some of these papers, particularly Braithwaite 2009 and then Agun et al., which is our group, 2013. Some arguments are given of roughly what the conditions should look like, but they don't give a precise criterion. And so the factors that are in front here are obtained from simulations, and they are also only approximate. And they might depend on exactly what the magnetic configuration is. So this is a very rough condition here, but it seems to approximately hold for these toroidal, poloidal, axially symmetric equilibria. But there are no rigorous analytical proofs of any of this, which would be very nice to have. But it is very complicated. In this Agun paper, we seriously tried something like that, and we didn't really get very far, because even to do some very special cases becomes very complicated. But yeah, well, if anyone likes to do those things, I certainly encourage people to do it. I would definitely like to see an analytic proof of all of this. But a consequence of this is that here, these two gammas are generally different. In the neutron star, they are not very different, but they are different enough. And here we have the gravitational energy of the star, the gravitational binding energy of the star, which is a very large number. So in principle, this inequality could allow for the toroidal component to be much stronger than the poloidal component, because we have this big additional number in here. And that means that there could be a strong hidden toroidal field in a neutron star, which on the one hand could be an energy reservoir for magnetars, and especially for the so-called low magnetic field magnetars. And it might also explain the non-uniform surface temperature of the so-called compact central objects in supernova remnant, which does not seem to be consistent with the magnetic field strength that is observed in these stars. Because, well, of course, the toroidal component you cannot see from the outside. You see only the poloidal component. You measure it by the spin down. So the toroidal component is hidden, and it might be substantially stronger than the poloidal component. But not forever. That is something that we will now address. Yeah. So how can we imagine the evolution of the magnetic field in neutron stars? First, a stable non-barotropic equilibrium will be established within a few Alfvén times. And the Alfvén time is something like 1 second for 10 to the 14 Gauss magnetic field. It becomes smaller for stronger fields and somewhat longer for weaker fields. And the time scale might be extended. It might be longer if the star is quickly rotating. Okay, it is complicated, but in a rotating star, the stabilization, the approach to equilibrium might take longer. But so this is the first point. In a very short time, we could achieve a non-barotropic equilibrium like those which we described, which Braithwaite found in his simulations. But then on much longer time scales, there are several processes which can sort of erode this equilibrium. And these were the processes that were initially cataloged, so to say, in our paper with Peter Goldreich, and which several of us have been working on later. In the crust of the neutron star, we have Hall drift and ohmic dissipation, which have been studied a lot and which I will not touch on anymore in here. And in the core of the neutron star, you have two different regimes in which the processes are substantially different. One is if the core temperature is bigger than about 5 times 10 to the 8 Kelvin, we are in what we call the strong coupling regime. With strong coupling, we mean that there are strong collisions between particles. So neutrons, protons, electrons, and whatever else have to be considered essentially as one fluid. However, also because of this large temperature, we will have weak interactions, the so-called Urca processes, which can convert particles into each other. And that means that on a long enough time scale, on time scales which are determined by these Urca processes, the matter inside the neutron star is not really non-barotropic. We can think of it as barotropic on long time scales, because as I move a fluid element, the composition of the fluid element will adjust to its equilibrium composition. And so on that time scale, I will have a one-to-one relation between pressure and density. So in that case, on a weak interaction time scale, we can have bulk flows in which all the components of the matter move together and can move the magnetic field around. Okay, so this regime is currently being studied by one of our students, Nicolas Moraga, who will so soon defend his master's thesis and write a paper on that. But in the present work, we are concentrating on the opposite regime, which is the regime of core temperatures less than 5 times 10 to the 8 Kelvin, and therefore most of the history of a neutron star, which is what we call the weak coupling regime. In this case, the collisions become weaker and the weak interactions become much weaker. So we can basically ignore weak interactions. Now we are not converting particles into each other, but since the collisions are weaker, the particles can diffuse with respect to each other. Different particle species can move with different velocity fields. This is what we call ambipolar diffusion, basically the motion of protons and electrons and possible other charged particles with respect to the neutrons. And this is what the paper that I will be discussing is concentrating on. So at this point, I'm finishing my introduction and I'm going into the paper, but I think it will not take too long now with this context to discuss the paper.
No, that's absolutely okay.
Okay, fine. Yeah, so here we are writing down the equations of motion for different fluid species. Here we have the neutrons. We have basically mass times acceleration on the left-hand side, mass per unit volume in this case, times acceleration. And here are the forces. We have this is essentially a pressure gradient. It's a gradient of the chemical potential of the neutrons. Here we have gravity, the gradient of the gravitational potential. And these terms are collisions between different particle species, which depend on the velocity difference between, in this case, neutrons and some species J. And there is some coupling constant, some gamma and J, which tells us how frequent the collisions are between those two species. And here we have the analogous equation for some charged species where we have the same terms again, plus the electromagnetic terms where here we have basically the Lorentz force. Okay, so now we are interested in processes that happen on very long timescales. Timescales, they are much, much longer than the propagation of sound waves, of gravity waves, of Alfvén waves inside the neutron star. So on those very long timescales, the velocities will be small, and the derivatives of the velocities, the accelerations, will be even smaller. So basically, we can think of the left-hand side of these equations to be equal to 0. We have achieved a hydromagnetic equilibrium. The fluid is in a non-barotropic hydromagnetic equilibrium. But now I'm studying only slow diffusion of different particle species with respect to each other. So we are setting the left-hand side of these equations equal to 0. Now, however, it becomes complicated to solve these equations because I do have these relative velocities here between different particle species, which mean that the particles will move, but they need to move from one non-barotropic equilibrium to another through a continuous sequence of non-barotropic equilibria. And so in principle, I could try to solve these equations self-consistently in order to find different non-barotropic equilibria, but that becomes very complicated. So what we do is a little trick in which we include an additional term here, which we first did in this paper, which addressed the one-dimensional case, but now we are doing it for in more dimensions. We are including this fictitious frictional force on the neutrons. So here, what this term, if I insist on interpreting it physically, this means that there is a friction of the neutrons against some background, some vacuum or whatever. But this friction we will take to be small. There is a coefficient in front which we will take to be small enough so that this friction allows us to go into an equilibrium state and then follow the successive equilibrium states, but without having an important effect otherwise. So I understand that this is fairly difficult to see why this makes sense. So let me try to think about a very simple model, a toy model, which is an analogy to this. So the analogy is a harmonic potential with a moving equilibrium point. So what do I mean? I have a massless particle that is subject to a harmonic potential whose equilibrium point has a prescribed motion, which I will call x of t. Okay, it's basically like I have a particle tied to a spring, but the other end of the spring is moving in some way that I'm prescribing. And I want my particle to follow the motion of this of the other end of the spring, to follow its equilibrium point. So I want y will be the coordinate of the particle. I want to be y of t to be approximately like x of t. And so I apply such a weak frictional force. I call this minus zeta times y dot. That will be an additional force that I add to the particle. So since the particle is massless, I'm ignoring the inertial term, and the mass is 0. But here I have the two forces. One is a harmonic force, which depends on the difference between y and x. I remind you that x is moving. some spring constant, and then I have this frictional force that I added here. And of course, from here, I can get a y dot in terms of the other terms. And this tells me then that y dot will be such that it allows y to approach x. So if y is smaller than x, this will be positive. And if y is larger than x, it will be negative. So y will be approaching x if I have this frictional force included here. So the particle will be moving towards the equilibrium. Now, however, I can't stress that this frictional force is weak. So this zeta coefficient is small. And in that case, I can check that this equation has a series solution, at least a formal solution, of the form y of t is equal to x, this is the lowest order term, minus zeta of k times x dot plus zeta of k over k squared times x double dot, and so on. I will have successive powers of zeta over k and successive derivatives of x. So if x varies slowly and zeta is small, in fact, from this equation, you can see that the time scale for y to approach x will be zeta over k. Right. And so if the frictional force is weak, this time scale zeta over k will be small. So I basically need the time scale for x to vary to be longer than the time scale zeta over k. And in that case, this series should converge. So in principle, so what I'm trying to show here is that if I add this frictional force, the particle will tend to first approach the equilibrium point and then follow the equilibrium point, and it will follow it more closely if zeta is small and x varies slowly. Okay, so those are the two effects of this friction force, which is supposed to illustrate what the effect of the friction force on the neutrons will be here. So the different forces acting on the particles will force some relative motion of the particles with each other. But this term then allows me to determine what will be the absolute motion of the neutrons, not just relative to the charged particles, relative to the star, if we want to see it in that way. And it will allow both of these force equations to remain close to zero over long time scales. And in this way, we will be following the equilibria. This is the approach that we followed in this paper. Now, in collaboration with Francisco, Alejandro Valdivia, and Michael, we are exploring different ways of solving these equations, which might be numerically more efficient. But this is the way we implemented in the paper, and it seems to work, as I will show in a moment. Okay, so doing that, we will get equations for what I call the ambipolar diffusion velocity, which is the difference between the velocity of the charged particles and the neutrons. And here we are assuming that we argued in the paper that the difference between the proton and electron velocity is very small. So we ignore this, which is what will give rise to the Hall effect. And we assume that all the charged particles, the protons and electrons, move with one velocity Vc, which is somewhat different from the velocity of the neutrons, which is Vn. And this difference is given by this combination, where we have the frictional drag coefficient between charged particles and neutrons here. And the neutron velocity is given by a similar equation, but with this fictitious friction coefficient here in the denominator. And we tried different values for the fictitious friction in order to make sure that it really didn't make a difference for the evolution. So the way we do the simulations is that we set up some magnetic field, some charged particle density perturbation, some neutron density perturbation. Then from those, we calculate these velocities from the equations that I just showed. And we put these into the induction equation for the magnetic field, where the magnetic field moves with the velocity of the charged particles. It moves with the charged particles. And we have the continuity equations for the two species of particles, charged particles and neutrons. And all this is linearized. We are assuming that these density perturbations are small, which is a very good approximation in the context of neutron stars. They should be something like 10 to the minus 6 or something of the total density. That also means that these two equations will much more quickly reach an equilibrium in which we don't have time derivatives anymore, in which the divergence becomes zero. That happens much more quickly than for the magnetic field to reach an equilibrium. The calculations are done on a spherical fixed grid. Here are the details, but you can look at the previous paper for details on that. And yeah, so we compared what happens if we have different values for the fictitious friction parameter. These change by a factor of 10. And what we have here is that, this is time in logarithmic units, and these are different quantities for which the RMS value inside the whole volume of the star is shown. So this is the RMS magnetic field, the RMS neutron velocity, the RMS ambipolar velocity, and the ratio of the ambipolar to neutron velocities as a function of time. And you see from the neutron velocity that at the beginning, you have velocities which are quite different depending on the fictitious friction parameter, which is natural because initially, here. Okay, I didn't say this. As an initial condition, we set the density perturbations equal to 0, just arbitrarily, just some initial condition, and we put in some magnetic field. So the two pressure gradients are 0, but the Lorentz force will be non-zero. And in that case, of course, the neutron velocity will be inversely proportional to the zeta parameter. And that's what we see here, that depending on zeta, the neutron velocity can be very different. But then you see that after some time, the neutron velocity will become pretty much independent, and at late times, very independent of the zeta parameter, which tells us that we are going towards an equilibrium state where this zeta parameter really doesn't matter anymore. The ambipolar velocity is affected very little by this parameter, and it also becomes smaller as we approach equilibrium. And the magnetic field, the RMS magnetic field has, for a while, vary in different ways depending on zeta, because the neutron velocity is different. But then eventually the magnetic field stabilizes at some equilibrium value, which is not orders of magnitude smaller than the initial value. You see the RMS value has been decreased by a factor of 2 or something like that. But in order to visualize this better, Francisco made these movies.
Andrea,
yeah.
May I ask a question to previous slide? About previous slide. These spikes in the velocities near the vertical solid line, they are associated with which effect? So everything is smooth more or less, and you see that when the velocity comes closer to this vertical line, time, at some moment of time, we have some, well, peculiar behavior of all the quantities except the magnetic field.
Yes. Yeah, actually, I don't remember whether we identified something special going on there. I guess Francisco is connected. Yeah, Francisco, do you remember whether something in particular happened at this time?
No, not really.
Okay.
Could be related to noise, maybe.
Yeah. Yeah. Okay. So yeah, I am. Yeah, it looks like we really don't know the answer to your question, Dima.
Thank you. Yeah.
It doesn't have to have. It doesn't seem to have a very strong effect, as you pointed out. The magnetic field doesn't really seem to do much there. We can take a look at the simulations that I will show now in order to see whether something happens there. Yeah. So the vertical lines characterize different time scales, which in the next I will go into a little bit more detail into this. Here we identified 4 different time scales for this. The first 3 are connected to this fictitious friction zeta. And the fictitious friction zeta, I remind you, the idea was that it allows us to approach hydromagnetic equilibrium and then follow the hydromagnetic equilibrium, the non-barotropic hydromagnetic equilibrium. And we distinguish 3 time scales because these 3 time scales are analogs to what would be the sound crossing time, the gravity wave crossing time, and the Alfvén wave crossing time if we had the full dynamics. With a zeta, we can choose exactly how long or how short we want these time scales to be, compared to the time scale that we are really interested in, which is the ambipolar diffusion time scale. The time scale on which the non-barotropic equilibrium is eroded, and as we will see, it evolves into a Grachafranov barotropic equilibrium. So this is the time scale that we are really interested in, but it is interesting to see what happens on each of these time scales. And here we chose them so that they were sufficiently separate from each other that we could see a difference, but not so separate to each other from each other to make the simulations non-feasible. So, as I said, we start out with 0 density perturbations and with a relatively complicated magnetic field. Here, the lines are the field lines of the poloidal field. You see some are dashed, which means that they have negative alpha values. Some are continuous, so they have positive alpha values. So we have a quadrupolar poloidal field here. And then the colors mean the toroidal field. And you see we have different signs of the toroidal field here as well. And on purpose, these were chosen not to coincide at all. And so we would get some interesting evolution. So in this initial condition, we can calculate what the ambipolar diffusion velocity is. And it looks like this. This is just the poloidal part. And this is the poloidal part of the neutron velocity. You see both of them look very similar, as they should, because they are both determined by the Lorentz force caused by this magnetic field at this point. And then we evolve this over many steps in which we use these velocities to adjust the magnetic field and the densities in order to see how they evolve in time. And so here I will show you the evolution over this first characteristic time scale, which would be analogous to what sound crossing would be in a real neutron star. You see density perturbations appear, which are quite similar for charged particles and neutrons. As I showed, the initial velocities were very similar. And not much has happened yet to the magnetic field. We basically have built up pressure gradients, which are of the same order of the magnetic field, but the charged particles and the neutrons move together. So we have not really explored the degrees of freedom from having them moving in different ways. So that's what we have there. So let's go to the next time scale. There we are. So now we will explore the time scale of gravity waves, which correspond to motions which adjust, which take advantage of the composition gradient in order to allow the pressure gradients of the two different particle species together to cancel the magnetic forces, the poloidal magnetic force. Unfortunately, this did not come out very well because the charged particles perturbations are dominated by what happens here on the surface. But you see, if you pay close attention, that now the density perturbations of charged particles and neutrons have become different, geometrically speaking. Okay, the magnetic field still hasn't changed very much. We have had only very small motion, but the two velocities have become very different. And you see that the neutron velocity is basically vortices. It's a solenoidal motion. It's not compressive anymore. Now we go to the next time scale, which is the analog to Alfvén waves. Here, the magnetic field will start rearranging on a time scale that is still dominated by this fictitious friction force. So now we are going towards the non-barotropic magnetic equilibrium, and this is what we will see here. Now you see that the magnetic field configuration, particularly the toroidal field, is changing. And the toroidal field is being concentrated into close poloidal field lines. And and so at this point we have essentially reached a hydromagnetic, a non-barotropic hydromagnetic equilibrium. Still, the ambipolar diffusion velocity is substantially smaller than the neutron velocity. So the fictitious friction is still important. Well, the so was not appropriate, but the fictitious friction was still appropriate in order to get into this equilibrium. But now we are in this hydromagnetic non-barotropic equilibrium, but we still have a degree of freedom to explore, which is neutrons and charged particles moving with respect to each other. And so we go to the next time scale now, which is the ambipolar diffusion time scale. And here we have additional motions. And basically what you are seeing here is a look at the scale for the density perturbations. The neutron density perturbations are becoming very small, whereas the charged particle density perturbations remained of order unity in our code units. And well, the magnetic field has not changed very much now, but we have reached a point in which the Lorentz force caused by this magnetic field is balanced by the pressure gradient of the charged particles only, because the pressure gradient of the neutrons has become very small. And so this is the last stage that we explored in our simulation, because now we got into a Grad-Shafranov equilibrium. I remind you that the magnetic field could be written in this way with a poloidal and toroidal component, where we had this alpha and beta scalars, where beta in equilibrium had to be a function of alpha. And so here we have beta as a function of alpha, and the chemical potential perturbations for the charged particles and the neutrons also as a function of alpha. And we are plotting the values of these two, well, the values of these combinations of variables for each of the grid points in our simulation as a function of time. So this is the initial condition. We had no density perturbations, and we had some complicated magnetic field where we did not have a clear relation between beta and alpha, far from it. But now we evolve this in time over the whole range of times that we saw in the previous movies. And you see now beta became a clear function of alpha relatively soon. And the chemical potential perturbations, the neutron chemical potential perturbation, it went through non-zero values, but now it became very close to zero for all values of alpha, that is everywhere in our grid. Whereas the charged particle chemical potential perturbations now became a fairly clear function of alpha. This is still running, but not much is happening anymore. Okay, so should I show that again in order to, so you register everything that is going on in this constant? Here, well, I want to point out, yeah, here, as I said, the toroidal magnetic field is non-zero only within the closed poloidal field lines. It's zero everywhere. So beta is zero in most of the star and non-zero only at this particular, these particular regions in the final equilibrium state. And that's also what we see happen here. Beta initially was non-zero everywhere, essentially. And, but now as we run the simulation, we see things, complicated things happening. But in the end, we have beta equal to zero for most alphas, which is for the open toroidal field lines, but non-zero only on the closed toroidal field, poloidal field lines. And the chemical potential perturbations went to zero for the neutrons and to a function of alpha for the protons, for the charged particles, I mean. Okay, and this allows us to construct the Grachov-Franov equation. We have, so in the final equilibrium state, we have an equilibrium between Lorentz force and charged particle pressure gradients. And we have zero neutron pressure gradients. And so the Grachov-Franov equation can be written like this. Now only for this first equation, for the equilibrium between charged particles and the magnetic field, with the same definition. And here we check the quantity that goes in the Grachov-Franov equation, in fact, goes to very small values at the ambipolar diffusion time scale. Whereas the magnetic field decayed a little because it had to adjust to this new equilibrium, but it did not decay very much. And I'm now seeing this is probably a different simulation than the previous plot because the value is somewhat different. We explored many different initial conditions. Only one of them or two are reported in the paper, but the results are generally similar. We see the evolution of the velocity fields here. Concentrate on the lower panel. Here we have the velocity of the neutrons, the charged particles, and the ambipolar diffusion velocity, which is the difference between the two. And you see first, charged particles and neutrons move essentially together. Then we reach a hydromagnetic equilibrium where their difference becomes of the same order as the individual velocities. And so we have some period of time over which ambipolar diffusion is important until at the end, again, the bulk motion is the main component of this. And this I tried to illustrate here, but maybe I should jump over this. Well, I'm almost ready. So here at late times, what we will have is that the divergence of the neutron flow and the charged particle flow will be essentially zero, because it's basically the magnetic field moving the particles around, but we are not creating accumulations, strong accumulations of particles anywhere. But these two equations, together with the fact that the neutron density profile and the charged particle density profile are different, don't allow neutrons and charged particles to move together. There has to be some difference between the charged particle and neutron velocity, which is the ambipolar diffusion velocity, and that is controlled by the proton-neutron collisions. And we had an equation for that before. So in this regime, we can use these equations to get the radial neutron velocity and the radial charged particle velocity in terms of the ambipolar diffusion velocity. So neutrons and charged particles move, contrary to our simple model in the Goldreich-Reisenegger paper many years ago. All the particles move, but they can't move only as quickly as the proton-neutron collisions let them move. So the proton-neutron collisions will limit what this ambipolar diffusion velocity is, and this in turn will determine what the bulk flow of neutrons and charged particles will be. So the bulk flow is proportional to the ambipolar diffusion velocity, but it is typically faster than the ambipolar diffusion, because the gradient in the numerator acts on smaller scales than this gradient in the denominator in each of these equations. And in that sense, we are confirming what two members of your group pointed out a couple of years ago. So the main results of our simulations is that a bit by construction, neutrons, charged particles, and the magnetic field quickly reach a hydromagnetic equilibrium, where here I should stress that this is a non-barotropic hydromagnetic equilibrium, where you have these buoyancy forces. On longer time scales, the neutrons and the charged particles move with slightly different velocities, controlled by their mutual collisions, which we saw. This is the ambipolar diffusion regime. And the neutrons asymptotically decouple from the charged particles in the magnetic field, whereas the charged particles in the magnetic field reach a final Grasha-Franov equilibrium, which would be a barotropic equilibrium. Now, of course, this raises some questions and motivates some further work. On the one hand, we would like more efficient numerical methods, which Francisco is working on with Michael, with Alejo, with me, in order to try to get this done. On the other hand, as I said, well, I mentioned before that in a barotropic star, we don't have stable equilibria. That is what previous simulations had shown. So this Grasha-Franov equilibrium that the charged particles reach together with the magnetic field, in principle, this should be unstable, unless we are not understanding something here. We don't see the instability in Francisco's simulations, probably because Francisco's simulations are restricted to axial symmetry. So what definitely needs to be done is to depart from axial symmetry in order to see these instabilities. Laura Becerra is in some way doing this with the pencil code, where she is, for the moment, trying to reproduce Braithwaite's results. So we want to check whether the instabilities happen when we think they should happen. And so far, it looks like they do. Maybe we should also run later an analog to Francisco's slow motion simulations in order to check whether the instabilities happen there too if we go into 3D. Another issue that should be explored in order to make actual predictions for neutron stars is to look at the temperature dependence of all these processes, particularly the collision rates, and the magnetothermal feedback, in the sense that if the magnetic field evolves, it will release heat and it will change the temperature evolution. We proposed a toy model for this in a paper last year by Marilyn Cruces and collaborators. But it is a toy model. We didn't really do any real simulations there, so I cannot. It's indicative that maybe ambipolar diffusion might be the reason for the weak magnetic fields of millisecond pulsars, but maybe not. This really should be checked. And Nicolas Moraga is working on some of this in his master's thesis, which is soon to be defended. And at low temperatures, we definitely have to include the effects of superfluidity and superconductivity. A model for this was proposed by members of your group. And this is something which should definitely include in our simulations, as well as the coupling between the evolution of the magnetic field in the core and the crust of the neutron star. So that's what I had to tell you. I thank you very much for your attention, for your patience, and for your questions. And well, I'm ready. Thank you very much.
Yeah, thank you very much. But questions will, well, the discussion is not over, and I believe that there will be some questions after the talk. Thank you very much, Andreas.
Thank you.
Very good talk, very clear for me. I enjoyed it very much. So what about questions? Well, does someone ask questions?
May I ask you one question?
Sure.
Yes, it's about spatial scales of magnetic fields, because it's some feeling, there is some feeling that it is maybe very close toroidal fields, and maybe just opposite, it is maybe just large cross-section of toroidal magnetic field. Which factors determine just a spatial scale of the field in your construction, your equilibrium construction?
You mean particularly the spatial scale of the toroid here?
Yes, just about it.
We have not explored that very much. One thing we have explored a little bit, which is not yet published, is that if we increase the strength of the toroidal field in in a torus like this, it will tend to spread. The torus will become bigger because you have a stronger magnetic force caused by the toroidal field, and so it will tend to spread. It seems to depend a little bit on the density gradients and on the geometry in general, because if you have strong stratification, you don't allow it to spread radially very much. So you will be spreading basically on spherical surfaces. So you could have a torus which is elongated parallel to the surface of the star. But as I said, we have not explored the details. It will probably depend on what the initial conditions are for the magnetic field, how you start off with, and then you will rearrange it somehow. There are some conservation laws associated with this. For example, well, here our induction equation has a very simple form. Well, I think I don't need to show it. The induction equation is basically telling us that the magnetic flux lines move with the charged particles. And in that case, we don't have any reconnection. And in that context, the toroidal flux within a closed boloidal field line will be conserved in time. And that's true for any of these closed boloidal field lines. So we have, and the boloidal field line, by definition, encloses a fixed poloidal flux. So there is a relation between the poloidal and the toroidal flux, which constrains the motion. I think this could be explored more in order to see what that tells us, but I don't know yet what it tells us exactly.
Yes, thanks.
Yeah. More questions? And may I ask, what do you think about the effects of general relativity? Can they introduce something new into this picture if you take into account, well, do it in general relativity?
I really don't know for sure. I would be very surprised if general relativity made a difference here. It will, of course, change the structure of the star a bit. It will probably change the structure of the equilibrium magnetic fields a bit. But I would be very surprised if it made a qualitative difference to any of this. But I have not explored that. And even people who have done some calculations of this in general relativity, I think they haven't found any substantial differences.
And introducing crust-core boundary and different physical, well, equations in the crust and the core.
Yeah, that can definitely make a difference. In what we did here, we modeled everything outside of the core as a vacuum, as a perfect resistor. And so if the resistivity of the crust is high enough to make the evolution timescales in the crust shorter than those in the core, then these simulations should be accurate. If that is not the case, if the crust is quite pure, if it is a very good conductor, then the magnetic field will be essentially frozen into the crust. And so that will impose a boundary condition on this. We will have poloidal field lines which are stuck in the crust in which the core cannot easily move. And so in that case, the crust would have a stabilizing effect on the magnetic field in the core.
Mm-hmm.
And we will probably have more complicated, more stable equilibria.
Thank you. Thank you. More questions, comments?
Andreas, may I ask, so do you believe that the final Grad-Shafranov equilibrium will be unstable?
Well, that's almost a religious question.
Even taking into account that the star is non-barotropic.
We have discussed this privately, but yeah, my guess, a semi-educated guess, would be that yes, that Grad-Shafranov equilibrium would be unstable. The growth time of that instability would be something like an ambipolar diffusion time scale. But we certainly have to check that and make sure that we really understand it. So far, it's more religion than science.
Mm-hmm. Okay. Is it difficult to check it using the existing codes?
I think yes, because we would have to extend this grid through to a third dimension. We would have to include the phi direction. Well, maybe we could do something different also, which is that Laura's simulation, where she is doing basically a classical MHD for stably stratified and non-stratified stars. That we could try to check whether there the instabilities depend on having deviations from axial symmetry. Maybe in those simulations we could somehow restrict them to axial symmetry and see whether the instabilities still happen. And that would give us some hint. If we get instabilities there in axial symmetry and we don't get them here, then there is something else to explain, which I wouldn't know so far how to explain. But yeah, there are several things to check, and I'm not sure for the moment.
Thank you.
Yeah, more questions?
There is a question in the chat actually. Andreas, do you see it? No?
Let me see how to do that.
There should be the chat panel in the bottom, or maybe the person who asked can say it, this question, or I can say it. So the question...
That's faster.
Okay, so the question from Felipe Zapeda, and the question reads, is there any way in which this work could be connected with the hotspots?
Well, I guess in a way, yes. Well, the hotspots on the neutron star surface are thought to be connected to the magnetic poles. And at least if we could extend these simulations to 3 dimensions, it could tell us how these poles would move and whether you could have equilibria which are not axially symmetric, where the poles therefore are not exactly opposite to each other. And of course, in that case, it would be particularly critical to have a realistic model for the crust as well, and not just for the core. I don't know whether Felipe had something else in mind with his question. Maybe Felipe can tell me.
No, it's just a general question.
Okay.
Thank you.
Thank you, Felipe.
Okay, more questions? Well, if not, let us thank Andreas again. Thank you very much, Andreas. Wonderful talk. It was very good. Well, so the seminar is over, and the next seminar will be next Tuesday at 12 sharp, and it will be a session of short PhD student talks, just for attestation.